All right, everyone, welcome back for session 2.3. We're going to take a look at some more graphs, graphs that are good, and we'll also take a look at some graphs that are bad. Okay. The key concepts of this section are to take a look at some more common graphs that are used, and we'll talk about some ways that graphs can be deceptive or misleading. And then, we'll talk about how, basically no one graphs by hand. Everyone uses technology to create these graphs. All right. First graph we're going to take a look at is called a dot plot. A dot plot is a graph of quantitative data. Okay, so remember that's going to be data where it's numerical. Right? And each data value is plotted as a point or a dot, that's where it gets its name, dot plot, above a horizontal scale of values. So here I've got a dot plot for us. And this dot plot represents the pulse rate of a bunch of male subjects. And when I look at this, I'm supposed to look at this and read this by saying that, oh, okay. So those are the 40s, those are the 50s, 60s, 70s, 80s, 90s, 100, 110s. These two dots right here, this dot right there being right above the 40 means we've had one person with a pulse rate of 40. Now that one right there, I don't really have a scale, but it looks like it's probably a 42. And then over here, I've got two dots right above 50, so that means two people with a pulse rate of 50, and so on and so forth. So basically what a dot plot does is it creates kind of like a histogram. It's just instead of having categories or classes that have any width to them, every single column here, so any one single column here like this guy, just represents one single pulse rate. In this case, that's probably what, 82? Yeah. And so each data value is plotted as a point above its place. So all of these are the 60s, all of these are the 70s, and so on and so forth. Now looking at this, if we look between 70 and 80, if that's 70, that would be 72, 74, 76, 78, 80. So it looks like whoever gathered this data set, that our original data set was only even numbered pulse rates. Now you might be looking at that and wondering, how could that possibly be? Someone could have a pulse rate of 55. I bet it was how they collected it. If they measured for 30 seconds and then multiplied that answer by 2, everything would be even. Or if they measured for 15 seconds and multiplied by 4, everything would still be even. So I don't think it was this, because if it was 15 seconds and then times 4, everything would have to be a multiple of 4. And so you couldn't have 42 as a pulse rate. I'm betting whoever gathered this data did this. All right? Now, I want you to think about what I just walked through and what I just said about this data. I've got a graph here that shows me trends, and it shows me that my data kind of does this number again. Okay? Maybe there's a little bit here missing, a little bit there, but generally kind of bell-shaped. Or maybe you could argue it's a little bit skewed to the right, where the center is kind of over here. But I was also able to read from this graph every single original data value. So while I can talk about the shape of the distribution, I can also recreate the original data list. So much so that I was able to see that there was an issue, that every pulse rate was even, and I could tell that it wasn't a times 4, that it had to be a times 2. So one of the values of a dot plot is that while it does give you the shape of the distribution, like a histogram does, it also allows you to recreate the original data list. Isn't that interesting? All right, stem and leaf plots. Some people call them stem plots. Some people call them stem and leaf plots. I've seen both. I personally prefer stem and leaf, but I understand both. Okay? This is that exact same data, the pulse rates for the males. But this time we're using a different type of plot where we're doing horizontally, where these numbers over here, these are referred to as the stems. And then these numbers over here on the right, these are referred to as the leaves of this. And so all of these values over here on the right represent the last digit in the data point, and the numbers on the left over here represent the rest of the digits. So when I look at this first row right here, I see a leading digit of 4, one terminal digit of 0, and another digit of 2. So those are the pulse rates for 40 and 42. Down here, what's that? Well, the leading is 10. The following, or the last digit, is a 2 and a 4. So that means there was 102 and 104. Right? And when I look at something like this 7s right here, when I read that, I read a 70, 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 a 72, 72, 72, 72, 72, 72, 72, 72, 72, 72, 72, 72, 72, 72, 74, 74, 74, 74, 74, 74, 74, 74, 74, 76, 76, 76, 76, 76, 76, 78, 78, 78, 78, 78, 78 for all those data values. So the idea behind a stem and leaf plot is pretty much the same idea as a dot plot up here. It's just that the dot plot kind of spreads it out a little more, and no one column in the dot plot is anything other than a single data value and its corresponding frequency. The number of dots would be its frequency. Whereas down here, every stem represents a class of data. So this stem right here, that represents everything between 40 and 49. The 5 is all the 50 to 59, and then so on and so forth. So all of the data values that exist in a row in this are a group of 10 in this sense. It's the 50 to 59. That's 10 values. All the 60 to 60, 70 to 70, 80 to 80, 90 to 100 to 109. So it's just a different way to display the data. What's better? I don't know. I don't think there is a better. There's just different ways to represent the data. And why do we have different ways to represent the data? I don't know, because we can. Right? What are these things good for? Well, stem plots do show the shape of the distribution. You can see that there's a peak right here, a lot of 60s. It's a little bit less here and a little bit less there. Okay? So it's kind of a little bit peaky, right? But it's turned on its side, so it's a little harder to see. It retains all the original data values. You don't have to think about it. Up here, we had to look at the scale to try to figure it out. Down here, you can just read them right out of there. And the data are nicely sorted. Right? So that's a good thing. Just another way to display data. Remember, none of this is about this is the right way or this is the best way. It's just there's different ways to display the data. It just depends on what information you want the user to have. Okay? Another way to represent the data is to use time series graphs. Now, time series graphs are used when you have time series data. Well, what's time series data? Let's go back to my Coke can example. And let's say that I'm concerned about how this machine is filling those Coke cans as the day goes on. Maybe when the plant opens in the morning, I think it's working right. But as the day goes on, I think it starts getting further and further out of whack, further and further away from putting that true 12 ounces in those cans. So I would gather time series data where this axis down here is going to be the time. Over here, I'd probably put the start of the day, or maybe the start of a shift. Over here, I'd have the end of the day, and maybe every 15 minutes, I would go down to the assembly line and randomly grab a can. Now, if my goal is right there in the middle, and if that's the 12 ounces, I'd like to see all the data right around that 12 ounces. But what if I saw something like this? Well, I would look at that and say, looks like it's trending down over time. So I don't know what's happening, but they're overfilling at the start and they're way underfilling by the end of the day. Right? So time series data is trying to tell you how something is changing over time. So here I've got a time series data that talks about law enforcement fatalities. Right? This is a number of people who died who I guess worked in law enforcement. horizontal axis is time, this time measured in years, whereas over here, I'd probably be measuring in hours. I've got years, and it looks like there's a general trend down. There's this one anomaly there. What would that be, like 2001 maybe? I don't know what happened in 2001. Maybe you could think of what happened in 2001 that would have increased the law enforcement fatalities. Wasn't 9/11 in 2001? So we probably lost a bunch of people there, what might have caused a little blip in our data there. But it looks like the overall trend is that the number of people who are dying, law enforcement fatalities, is going down over time. Right? So what we're looking for is we're not looking to tell how many necessarily. We're looking for those time trends. How is it changing over time? Is something going up? Is something going down? Is there a change? Is it flat? Is there no change over time? So a time series graph attempts to answer that question. Okay? Bar graphs, another way to display data. Bar graphs are great for our categorical data. So if we have categorical or qualitative data, bar graphs are a great way to do it. I've got a lovely bar graph here that talks about, let me move this out of the way for right now, that talks about the number of stolen boats by type of boat. So my horizontal axis down here is categories. Now, one way that you can tell that this is not a histogram is the bars don't touch. And the reason the bars don't touch is because it wouldn't make sense to have the bars touch. Each of these is a separate category all in itself. And then I look at this and go, looks like jet skis are the most stolen at about 1,400. And it goes down from there. Pretty much nobody's stealing any sailboats. Okay? Jet skis and motorboats, those are what's getting stolen. 1,000 and 1,400 or so. Okay? So I got a bar graph. A bar graph is good for categorical data. It represents how many. We've got frequencies on the vertical axis, and then we have our categories on the horizontal. Okay? Actually, this isn't a bar graph. This is a Pareto chart. Now, a Pareto chart is just a bar graph, but it's a bar graph where you order the categories across the horizontal axis from the most to the least. So one could look at this graph and say, hey, that's a bar graph. And they would not be wrong. But another person could look at that and say, you know what? That's actually a Pareto chart. And they also wouldn't be wrong, because a Pareto chart is just a fancy bar graph where everything is listed from highest to lowest. Right? If you've ever taken a biology course, if someone looked at a chimpanzee in the zoo and said that that was a mammal, is that how you spell mammal? M-M-M-A-L, mammal, they would be right. And someone else could say, oh, it's better than a mammal. I can say that that's a primate. Okay, well, they would also be right, because a primate is a type of mammal and a chimpanzee is a type of primate. Right? And if someone else went further and said, oh, that's a great ape, well, they would also be right. Chimpanzees are great apes, right? Chimpanzees, gorillas, and orangutans, the great apes? Yeah. It's a great ape. And they would also be right, because it is just a more accurate description of those. And someone could probably come in and give us the actual scientific species and genus name for those, and they would also be right. So a Pareto chart is a fancy bar graph. Bar graphs are great. They are one of the few ways that we can actually graph categorical data, so we use them a lot. And to make something a Pareto chart is just to say, hey, I want to have a bar graph, but I want to order it so that they go from highest to lowest frequency. Right? I mean, what's the purpose? Well, you could argue that it draws attention to the more important categories. I don't know that I agree with that, though. Because if this big bar right here for jet skis was over here in the third position instead, and my graph looked like this, where this bar was the tallest, and that was jet skis, I would still argue that that big bar, that this being the largest bar, would still stand out. So I'm not sure that I agree that it draws more attention to the important categories, but I will agree that it's a choice. It is a choice that one could make that orders the data from high to low. Not good, not bad, not better, not worse, just different. Right? Pie charts are the other way, the other good common way that we can represent categorical data. So categorical data are represented by slices in a circle. Slices is an interesting word. Technically, these are called, the word just flew out of my head. They're not called slices. They are called sectors. Slices is, slices are what we call them when it's a pizza. These are sectors of a circle. But if you call them slices, no one would argue with you. And the idea here is that the relative size of a sector or a slice depends on the proportional frequency. So if I wanted to know exactly how big this is, like how many degrees that is of that circle, I would say, I've got to go back to the data, find out how many jet skis were stolen, so the number of jet skis, divide that by the total, and then multiply that by 360 degrees. Now, 360 degrees is all the way around a circle. So if the number of jet skis divided by the total was half, I get 180 degrees. Now, this sector here that's blue looks like it's a little bit shy of half. I would guess, if I had to, I would say it's about 170 degrees. So then if I was drawing one of these, I'd get out my protractor and I'd measure out 170 degrees and I'd shade that in and call that jet ski. And then down here, the other big piece, motorboat. I would take the number of motorboats, divide that by the total, times 360 degrees, and that would give me the relative size, that angle, that central angle for motorboats, and so on and so forth for all the different categories in our data set. Now, let's be honest though. No one is busting out a protractor and doing this. Every graph that we've looked at so far, no one is drawing these things by hand. We don't draw these things by hand. We let somebody else do that. We find some sort of technology, whether it be Microsoft Excel or Google Sheets, a spreadsheet technology, or an online website that makes graphs for us. We would input our data, select the type of graph, and have it make a graph for us. Okay. Another type of graph that you could make is something called a frequency polygon. Do you remember the data from last lesson about the lunch time at McDonald's? We made a histogram last time. This is a frequency polygon. But if you look, the histogram is right there. There's the histogram. It's hiding underneath the frequency polygon. So one could argue that a frequency polygon is just a histogram if you're too lazy to draw the bars. The only significant difference is when I did the histogram, I didn't put anything below 99.5, whereas this goes down to the axis at 49.5, and it goes down to the axis at 349.5. Now, if I go back in time to McDonald's, which was way back here, there was nothing below that lowest bar. There was nothing over here at 49.5, because in a frequency polygon, we send it down to 0 here, and we send it down to 0 here to say nothing is on the low end and nothing is on the high end. So the only real difference that you're going to see between a histogram and a frequency polygon is they're going to be a little bit wider because they've got to go out one class beyond where the last bar was for the histogram and where the last bar on the high end was for the histogram. Right? Now, this is a frequency polygon because the vertical axis over here represents the actual count for the McDonald's information. I could make a relative frequency polygon by just converting that axis into a and I'm going to try to write this sideways, relative frequency by converting all those into percent. And if I remember correctly, that was 10%, and that would be 20%, and so on. Wasn't it 50 in this whole? Yeah. Okay. Now, why would I do a relative versus a frequency? I don't know, because I wanted to. Because these things aren't about this is the right way to do it and this is the wrong way to do it. These things are all about, I want to display the data. Here's how I want to display the data. I don't want to draw bars. I want to draw dots and connect them with lines. I'll make a frequency polygon. Ooh, I do want to draw bars. I'll make a histogram. Oh, I want to draw a circle and chop it up. I'll make a pie chart. Oh, I don't want to draw a circle. I'll make a bar graph. Ooh, I want to line my stuff up from highest to lowest. I'll make a Pareto chart. Oh, I don't want to line myself up. Oh, I have time series data. Now, this is probably the only one where the data tells you what you have to do. Because my data will always be two values, a time and then a number, a count or whatever it is, whether it's the amount of soda in the can or the number of fatalities. Because my data is going to be two values, an ordered pair if you want to get fancy about it, this is the only data that's going to force me to use a specific type of graph. I can only do a time series graph with that kind of data. With most data, you have choices. Okay? Now, when you have choices, though, you want to make sure those choices are good. One of the most common ways that people use graphs to deceive is to use a non-zero vertical axis. Okay? Now, this is a graph that was grabbed off of TV. I grabbed this off of, it was grabbed off of a baseball game where they were talking about this pitcher and they were talking about the speed of their knuckleball. And when you take a look at this graph, upon first inspection, you would look at this and you would say, wow, if I label these 1 and 2, the speed of his knuckleball really dropped off from 2012 to 2013. Because that bar for 2013, this bar right here, is really small compared to this bar right here. But then if you stare at it a little bit longer, we're talking about a 2 mile per hour difference. But does that graph show that? Because when I'm looking at that bar, I would say that this one looks like it's half as big. So if this was 77 miles an hour, this one should be like, I don't know, 38 miles an hour? Because it's like half as much, but it's 75? Yeah, someone whomever it was that made this image wanted to make it look like this dude was not doing well, that his knuckleball was really terrible this year versus last year, when in reality, it's only a 2 mile an hour difference, right? So without having a vertical axis that starts at 0, where this would be 77.3, and then you'd have to put 75 right there, so this bar would have to be like that tall, you can really make a very deceiving graph, right? There's lots of ways to make deceiving graphs. This is one that came out of Florida. This is the Florida Department of Law Enforcement, and I got this from Reuters, okay, which is a pretty reputable news site, so you'd think it would be a good graph. So let's look at what they're saying here, right? They're saying that in 2005, Florida enacted a stand your ground law. Now, the stand your ground law in Florida basically says that if someone comes at you, you don't have to try to run away. You can use force to protect yourself, right? And then this graph is showing the number of deaths by gun in Florida. Now, every gun death is a horrible thing. I am not in any way glorifying gun deaths. I am pointing out a really bad graph. Because if you look at what's happening on the graph, it appears that as soon as they enacted that law, that the number of deaths went down a lot because the graph moved in that direction. But then if you look at it a little bit longer, you'll notice that whomever it was that made this put the scale upside down. Instead of going down meaning less, going down means more. So this, what looks like a drop in gun deaths, actually means that it went from about, what is that? Maybe 520, 530 to over 800, 820 maybe. So there was a significant increase, about 200 more deaths occurred. But is that what you saw when you first looked at it? Okay, so here's my question to you. Is this graph lying? Or is it just misleading? And what's the difference between those two words? Well, if these data points are plotted accurately for this horrible axis, it's not a lie. But it's definitely misleading, because most people, if you've gone through K-12 education and taking any sort of algebra class, when you look at axes, your X and Y, you think that this way is an increase and this way is an increase. And if you think that up is increase, then you would argue that down is a decrease or left is a decrease. So this is definitely misleading. I find it incredibly sad that someone like Reuters would put this out, because its pure intent is to try to mislead the public. All right. So in conclusion, for most of this chapter, the idea was for 2.1, 2.2, 2.3 is that graphs are things that we do. We use graphs to display data because piles of numbers are ugly. What type of graph you choose, what type of graph you use, it's completely up to you. There are many useful graphs, and there are many other useful graphs that we didn't even look at in here. There's lots of them out there. There is no way that we could have one chapter that would just be, here are all the graphs possible, right? But what you want to do is you want to make sure that if you have data and you are going to display it, if you're going to have some sort of visual display of data, that you do it appropriately. If you have a small data set, don't even use a graph, just use a table. Because for a small data set, and this, we're putting 20 in there, but if you had 25, I would still consider that small. I don't think there's a good number to put there. But if you had a small data sets, just put a table in, give them the data. Okay? The purpose of a graph should be to focus on the nature of the data, right? Don't make it overly distracting, right? Don't distort data. Make a graph that tries to reveal the truth, the true nature of the data, right? And the ink in the graph should be used for the data, not for making it pretty. If you spend too much time making it pretty, it just makes it harder to read for most people. Right? That brings us to the end of section 2.3. Have a great day.